Lesson 10.2 is all about Pascal's triangle and the related patterns. Pascal was a mathematician that did all sorts of stuff. He was also the chameleon in Tangled, if anybody's a fan. So if we look at this triangle, take a moment, you can pause if you want and just look at what patterns you see. So one big thing you probably saw first is that every row starts and ends with a 1. So if you look at, let's say, this row here, 1 at the beginning, 1 at the end. The whole triangle is symmetric, meaning each row is symmetric. So 1, 6, 15, 20, 15, 6, 1. So it repeats the same values on either side of that middle term. Every term is the sum of the two terms above it. Meaning that, I don't know, let's go somewhere random. And the ones don't really count, right? So if we're starting up here with the 1 and the 1 and the 1, the ones are automatic. But starting with row 3, if you go below it, 1 plus 2 is 3, 2 plus 1 is 3, and then you fill in ones. 3 plus 3 is 6, 3 plus 1 is 4, 3 plus 1 is 4, fill in ones, okay? And that'll work anywhere. If you go down here, 21 plus 35 is 56, 56 plus 70 is 126, that works everywhere. Last piece, the second term is the same as the row number. Not there, the row number. Meaning, starting up here at the top, there is no second term. So this is row 0. Row 1, second term is 1. Second term is 2. This is row 2. So the row numbers essentially show up along this diagonal, if you'd call it a diagonal when the whole thing's a triangle. So for example, you can go to any given row, like this one here, look at the second term. This is row 8. So take a minute and you can pause if you want. Once again, fill in the row below. So fill in the 11th row. So for example, we would have ones on either side. 1 plus 10 is 11, and you go from there. You can go ahead and pause. Okay, so you should end up with 55, 165, 330, 462, 462, if only I wrote smaller, 330, 165, 55, 11, and 1. Okay, and we could like fill this in and make a nice picture. If we felt like it. That would be a continuation of our Pascal's triangle, but my pictures are bad as usual. So let's look at these values. So 5C0, you can use your calculator for all this. As a reminder, with your graphing calculator, you go to Menu, Probability, Combinations, and you end up with NCR and this blank here. And in that blank, you put, for example, for 5,0, you would put 5, 0 in there, okay? So you can use your calculator for this, or you can do it by hand. So this would be 5C0, would be 5 factorial over 0 factorial times 5 minus 0 factorial. 5C1 would be 5 factorial over 1 factorial times 5 minus 1 factorial. 5C2 would be 5 factorial over 2 factorial times 5 minus 2 factorial. 5C3, might as well finish it off for you, 5 factorial over 3 factorial times 5 minus 2 factorial. And then 5c4 was 5 factorial over 4 factorial times 5 minus 4 factorial. Okay, so our values, either simplifying that way or using your calculator, are 1, 5, 10, 10, 5, 1. And as far as that formula I did up here, we learned this in, I believe, 10.1a. Might have been 10.1b. I believe it was 10.1a. Okay, so you can go back and look at those notes if you forgot how to use it. So let's examine row 5 of Pascal's triangle. 1, 5, 10, 10, 5, 1. Let's look at row 5. Oh, look, it's 1, 5, 10, 10, 5, 1. They're the same. Okay, the same. So basically, Pascal's triangle, each row of it can be written as a sequence of combinations. So if we want to write row 4 as a sequence of combinations, we'll start with 4c0, and then we'll have 4c1, 4c2, 4c3, 4c4. And if you're wondering how do we know where to start and end, well, 4 is going to be our n. We start with 0 and we go till we don't have any more. You can't choose more than 4 from 4. Let's look for 70 in Pascal's triangle. So 70 is right here. And we want to write this as a combination. This is row 8, so it's going to be 8c. And if we go along here, this is 8c0, 8c1, 8c2, 8c3, so 70 must be 8c4. So our n is 8 and our r is 4. Let's look for 28. I guess there's 2 of them. So if we look for 28, there's one, and there's one. So this one right here, well, our n, it's row 8, so it's 8c, and this would be 0, 1, 2, so 8c2. 0, 1, 2, 3, 4, 5, 6. 8c6 would give us the other one. So 8c2 and 8c6. And so it seems weird that they're the same, so let's check out the factorial formulas. So 8c2 would be 8 factorial over 2 factorial times 8 minus 2 factorial. Now if we simplify that a little, we have 8 factorial over 2 factorial times 6 factorial. 8c6 is equal to 8 factorial over 6 factorial times 8 minus 6 factorial, which is 8 factorial over 6 factorial times 2 factorial. Point being, we have an 8 factorial and then a 2 and a 6 factorials on the bottom. Same thing here. So they're equal. We already did this. I jumped ahead. Okay. We filled in the next row by adding the 2 terms above each number. And when you fill in the sums of each row, there's actually also a pattern. So pause for a moment and fill in the sums of each row. And by sums of each row, I mean add up all these. So the sum of this one would be 1. 1 plus 1 is 2. 1 plus 2 plus 1 is 4, etc. Sorry, I didn't mean to skip, but you have your own page, right? So pause for a second and find all those sums. And what you end up with is row 0 has a sum of 1. Row 1 has a sum of 2. 2 has 4. Row 3 has a sum of 8, row 4 has a sum of 16, row 5 has a sum of 32, row 6 has a sum of 64, row 7 has the sum of 128. We don't have to write any more down. So if we look, there's a definite pattern, okay? So each time the sum is multiplying by 2 as the row increases by 1. So recursively, or depending on the one before it, you can multiply by 2. But if we want a general formula, we can think of our row as n, and then to find the sum, it's 2 to the n. So the sum of row 0 is 2 to the 0, which is 1. The sum of row 1 is 2 to the first power, which is 2. The sum of row 2 is 2 squared, which is 4, 2 cubed, etc. Okay? Because it's multiplying by 2 each time. And so what would be the sum of the numbers in the 15th row? It sounds hard, right? It sounds like we have to add up all the numbers, find the 15th row, but we can just do 2 to the power of 15 on our calculator, which is 32,768. So some properties of Pascal's triangle, we already talked about this, but just kind of have them all in one spot. The first and last terms in each row are 1. Don't worry about this. The second and next to last terms in the nth row equal n. So in the second row, the second term, let's look at this, actually let's talk about like the 7th row, right? So for the 7th row, the second term should be 7, yep, and the second to last term should be 7. Yep, that's true. Each row is symmetric. Get rid of this. And the sum of the terms in each row is 2 to the n. I'm going to skip the proof. If you want to see it, feel free to come to office hours and I'll show you, but in general it's pretty confusing, so I don't want to show you not in person.